My presentation is about the research, biocomposite of PLA and mango seed waste, potential material for food packing, and a technological alternative to reduce environmental impact. This work started in 2015 to the present day, and it's a multidisciplinary and multi-institutional, where Embrapa and its partners developed the reuse of waste from the mango juice agribusiness as a filler in the PLA matrix, developing new biocomposites wind casting, extrusion injection, and compression molding techniques. The partner institutions are the Mineral Technology Center, the Federal University of Rio de Janeiro, Rural University of Rio de Janeiro, the Federal University of São Carlos, and the National Institute of Technology. The studies developed by the team have already been published in the scientific community. The residues generated by the fruit pulp industry can represent an environmental impact since they are disposed inappropriately. Brazil is the world's third largest producer of mango, resulting in the generation of large amounts of waste, which is a potential raw material for the production of biodegradable materials. Mango seed was obtained through thermal processing and was separated into its fraction, kernel, and improvement, which added flatly as a filler to the PLA matrix, generated the biocomposite through extrusion injection techniques. The specimens were standardized by ESTM G638 Type 1. Table shows the mango seed part properties and biocomposites density on a dry basis. The ideal strat was identified only in the integument. NDF, ADF, ash mount, moisture content, and the protein density value are higher in the integument than in the kernel. Nonetheless, low moisture content was observed, which contributed to the material conservation. Additionally, the process of obtaining biocomposite by extrusion injection also destroyed and microorganisms that may be present in the material. As expected, carbohydrate contents are higher in the kernel than in the integument, and it can also be seen in the table 1 that the biocomposite of PLA mango residue present decreased densities if compared to the mango residue. The addition of cellulose-rich phases acts further diminishes the sample density. These figures show the particle size distribution of integument and the kernel determined by light scattering, and it also shows the scanning electron microscope image of them. The particle size distribution was greater than that observed in the CEM image. Mango's integument is about 207 micrometers, and the kernel is around 44 micrometers. The results differ probably due to the particle aggregation, which can be minimized by dispersing the fibers in a fluid. The image of mango integument and the kernel show the fibrous aspect due to the hemicellulose and lignin is distinctive. Although fibers are micro-sized and exhibit an irregular shape and size, we can also see that mango integument fiber present a heterogeneous fibrous morphology and the kernel present a homogeneous granulometric distribution, where they present a spherical ellipsoid shape. As we can see in this figure of the RIG profile was not significantly modified in the presence of integument or kernel in the extrusion injection process, turned to crystallized PLA into amorphous. The amorphous PLA present alloy centered at 2 theta around 16 degrees, which is the characteristic of structured PLA. We can also see that Both of integument and the kernel are present in the biocomposites, and they maintain their crystallized structure, since they are traces of crystalline cellulose appear at 2 tera around 22 degrees, and there are traces of starch showing peaks at 2 tera 17 degrees. Here we can observe the PLA biocomposite CAM image. Cellulose fibers from mango integument and the starch granule from mango kernel are specified in the PLA matrix. PLA integument, PLA kernel, and PLA integument kernel biocomposites show typical composites, typical characteristics with low interfacial interaction. There are cavities at the interfaces between the cellulose fiber and starch granules with PLA matrix suggests low compatibility. This behavior is explained due to the hydrophobic character of PLA and hydrophilic characteristics of the fibers. This low compatibility was expected since no compatibilizer was used in this formulation. As can be observed in these figures, the FTIR spectra showed the presence of cellulose, lignin, and starch in both integument and kernel. Nonetheless, more bands, most likely related to starch, were found in the kernel than in integument, while more cellulose bands were found in the integument than in the kernel. Any cellulose was found only in the integument. The FTIR spectrum also showed that the biocomposite had a remake correspondence, although with varying intensities. Here we can see the result of TGA-DTG. The weight loss profile of the integument exhibits two major events and was attributed to the evaporation of surface-bound water, natural humid, present in a low weight loss. The second event could be attributed to the cellulose degradation process, where a major weight loss was observed and confirmed from the DTG curve. In the mango kernels, TGA curve, it is possible to observe that this thermal decomposition occurred in three main steps. The first related to water loss. The second degradation step corresponds to a major weight loss and can be related to starch or lignin thermal degradation. In this step, the starch chain scission occurs, as well as the oxidation of glucose rings due to thermal degradation. The last event is related to the decomposition of cellulose polyoxines. Finally, TGA-DTG analysis of the niche PLA and biocomposites show that all samples express a weight loss at 100 degrees Celsius, mainly attributed to water evaporation, and the decomposition of biocomposites is completed at 350 degrees Celsius. It can be assumed that the addition of manganese residue causes a decrease in the biocomposite degradation temperature, likely due to the presence of cellulose and lignin components, which present lower thermal stability than the PLA matrix. Furthermore, with the increase in the lignocellulose components content in the sample, the more significant the decrease in the biocomposite thermal stability. Now we can observe the studies of thermal properties from GSC and of niche PLA and biocomposite with mango residue. GSC analysis identified the probable presence of cellulose and starch both in mango's kernel and integument, although higher amount of starch in mango's kernel and higher amount of cellulose in mango integument could be observed. The biocomposite presence all in the PLA transition in the first heating and subsequent cooling. Nonetheless, their TG and TM slightly decreased, showing that the fillers interfered in the PLA crystals organization. As a result, all biocomposite present higher crystallinity than neat PLA, and the highest value of crystallinity index was obtained for the biocomposites PLA 20 weight percent kernel. Moreover, in cooling, all biocomposites start crystallization in higher temperature than neat PLA, that is, first than neat PLA. Thus, it can be stated that cellulose and starch act as a nucleating agent for PLA. In this figure, I show the mechanical analysis of PLA biocomposite and the most significant improvements in mechanical property and various properties were obtained upon incorporation 20 weight percent integument, which present an increase to up to 38% in elastic modulus. The addition of mango's integument and kernel to PLA resulted in an increase in the elastic modulus of all formulation, which was already expected by the addition of rigid filler in the polymer matrix. Therefore, it was expected that introducing a rigid filler would increase the elastic modulus and maximum strength by a decrease in elongation was also expected. However, the extent of thermo-oxidative degradation of the filler kernel at the processing temperature may have caused significant disruption of glycoside bonds of starch, reducing their molecules to sugar. In this study, 6 biocomposites based on PLA mango waste, integument, ore, and kernel were successfully synthesized by an screw injection process and characterized to be used for rigid package, as well as proving an alternative to reduce environmental impact. The most significant improvements in mechanical property and barrier property were obtained upon incorporating 20 weight percent integument, which present an increase to up to 38% in elastic modulus. Therefore, this study suggests that the developing PLA integument biocomposites have potential as a new material for a rigid food packaging system. Thanks for your attention.